2 p.m. in Chicago, which means it's time for Vamos. We're very fortunate today to have as our speaker, Professor Prineha Narang from the Harvard School of Engineering and Applied Sciences. She did her PhD at Drexel and then got her PhD from Caltech in quantum plasmonics and nitride optoelectronics. And
I think you just gave me an extra PhD, but that works too.
Did you not get your PhD at Caltech?
I did. Keep going. Just keep going.
Sorry. She was then
more coffee.
a Ziff fellow at Harvard and an MIT research scholar in condensed matter theory. She really has all the awards, but just to name a couple, she's an NSF Career Award recipient, a Moore Inventor Fellow, MIT Tech Review Top Innovator, Forbes 30 Under 30. We're Facebook friends, so I happen to know that she's as deeply obsessed with triathlons and running as I am with cats, Brazilian Jiu-Jitsu, and drones. So that's, I would say, really saying something. I have to say, I've been really looking forward to this talk for quite some time because my feeling is that Pri thinks about problems in strongly correlated many-body systems, much as we do in the AMO community, but she comes at them from quite a different perspective. We're focused on building from the simplest building blocks we can and then asking questions about strong correlations. Her systems often have some of these strong correlations inbuilt, and then the challenge is to develop tools to understand them and distill out some pristine degrees of freedom to use for quantum science or applications. So I think there are really wonderful opportunities here to find some synergies between the fields and also potentially, to borrow the tools that she's been developing or gain inspiration for problems that we could explore in our systems. So let me just say you can post your questions either on YouTube or in the Q&A. There will be 2 breaks during the seminar for us to address your questions. So Pri, with that, please take it away.
Awesome. All right. Thank you so much for having me here virtually. I look forward to very soon a day where we can do this in person, but I still enjoy being able to give these to a broader set of audience from, well, the comfort of my office now. So I'm excited to tell you about the work we've been doing in predicting correlated and non-equilibrium light matter interactions. Before I start, I want to acknowledge the set of students and postdocs who worked with me on many of these topics. Some of these students and postdocs are now going on to start their own groups. And of course, an incredible set of collaborators across the US and across the country, now across the world. All right, so as John mentioned, if there are questions, please drop them in. I won't be able to monitor the chat, but I hope that there will be questions and perhaps even some leading questions that allow me to start collaborations with many of you and add your name to this list. So we take a broad view of predicting and controlling quantum systems, and we've developed approaches in QED, in particular in formally and computationally merging methods from QED with correlated electronic structure. I'm going to tell you a lot about that intersection in the talk here today. In particular, I'm thinking about cases where we can't easily separate out the light and the matter component, and in fact, keeping them together at the same level of theory is in itself a challenge. Okay, we think about how these methods can also leverage in some ways OQS, open quantum system approaches. The way to think about it is that, when I have a quantum system, I have the environment. I could think of everything that is going to the environment, whether energy, information as a one-way street, goes away, never comes back, or it could have memory, and perhaps if I get really clever, I can use that memory of the math in some way that is actually useful. Or I can think about methods from OQS as a way of describing strongly correlated systems at a larger length scale. And both of those are things that we're thinking about, the latter being something that one of my postdocs, Dr. Kadeh at Marsden, has been developing quite extensively. When we compute stuff, it's natural to say, well, we should be leveraging the latest, greatest algorithms, and we do. We also develop some algorithms. We think about how we can both use really, really large scale classical computation. We run calculations on the Summit supercomputer. We also now try to run tiny calculations on actual quantum devices. The hope being that perhaps there are interactions that we can capture, things that we can simulate that you wouldn't be able to otherwise. Some of these things are towards a broader goal of making scalable quantum systems a reality, whether it's networks, computing, or sensing. If you want to read more about our view on this, you're welcome to take a look at the camera that I linked to. So when I tell people that we predict stuff, we predict the behavior of quantum matter, there's this expectation that I have one technique, one magic acronym to rule them all. And I don't. In fact, nobody in the community does. If you want to go all the way from interactions and systems on the left all the way to the right, in particular, thinking about approaches from quantum chemistry on the left and condensed matter on the right, there's a real divide that needs to be bridged. In particular, for us to think about these potential energy surfaces, thinking about their interaction with the cavity and how perhaps the cavity could modify these potential energy surfaces, those techniques don't easily generalize if I say my molecule is now replaced by, say a interesting topological material. So this is famously referred to as the finite extended system divide across quantum chemistry and condensed matter materials physics techniques. And we're trying to figure out how we can synthesize approaches from across the spectrum to better predict stuff. In some cases, we've gotten lucky where we think about these defects that look like molecules that are trapped in a solid. They're very, very, their orbitals look very molecular. But some other cases where we're not so lucky, we think about how these can be formally and computationally merged. So the word correlations means lots of different things to different people. And I was told to, in this talk, make it accessible to students, postdocs, folks who are not necessarily experts in the field. So I want to spell out for you what correlations mean to me. The most common type of correlation that people think about is the electron-electron interaction, the strongly correlated electron problem being something that many on this call have thought about quite extensively. It's not the only type of correlation that we're interested in capturing in quantum matter. Turns out that the interaction with the lattice, the electron-phonon interaction, becomes incredibly important for us to describe excited state behavior, to describe behavior at finite temperature, and also to describe various types of optical excitations in quantum matter. And this is where I'd like to say there's a case to be made for diagrammatic methods where you can actually pick what level of theory to treat what part of the problem on. Say some cases you're interested in the electron-phonon component, you're interested in also thinking about some of the nonlinear photonic processes. That is a very different regime than trying to treat the electronic correlations at the highest level of theory possible. And in part, splitting it up in terms of diagrams and then computing diagrams at different levels of theory so you can get your electronic states from your favorite level of electronic structure theory. You can get your phonons, whether you want to do that within a density function perturbation theory, you want to get your phonons from some experiment. All of those things can still be harmonized in the context of this diagrammatic set of diagrammatic approaches. And if there's one thing you walk away with from my talk today, it should be that phonons are cool, phonons are important, they're a little bit underappreciated. And in fact, if you can describe some of these interactions, particularly past leading order, lots of interesting things become possible. Okay, nobody seems scandalized so far, so I'll keep going. A genre of correlation that doesn't come up quite so frequently in the same breath as talking about the electron-electron or the electron-phonon interaction is where we think about correlated light-matter interactions, right? So when we think about a polariton being formed, this is an AMO community here, so I may be repeating things that you've seen in courses, but this is truly a hybrid light matter quasi-particle. And you have attributes that come from the light constituent and some that come from the matter constituent. And frequently, separating those two out, particularly when you describe them from a theory standpoint, is unphysical. Polaritons come in various flavors. You can think of them as your favorite latte flavor. And they could involve simple things like plasma polaritons, where you can maybe parameterize using the dielectric response, things like phonon polaritons, where you're thinking about interactions in the near mid-IR, or cases where things get more exotic, like Cooper pair polaritons, Magnol polaritons, et cetera. These don't just have to be individual kind of separated out flavors. These can actually come in various forms all at once in some cases. So there are plasma phonon polartons, you can have exciton and magnetic polartons in some cases jointly. And this is not a comprehensive list. There are many, many more. So one of the things is a recent extensive review from Dmitry, not cited here actually, that goes through the nomenclature across AMO and condensed matter in all of the types of polaritons that people have been exploring. So I encourage you to take a look at it, because I think it really provides a fairly comprehensive view. One of the ones that I found quite exciting out of that view was the axion polariton, first predicted by the late Chucheng Zhang, that actually is now showing up in some of the topological systems we've been looking at. So that's a little Easter egg for you to remember for when I get towards the end of my talk. Okay, so there's excitation of the polaritons. There are new probes being developed. And this is where, as somebody who does theory and computation, rubber really hits the road. There's a very broad spectrum of excitations we've been looking at, in particular, new kinds of terahertz techniques, X-file techniques that have been introduced. And computational methods, conventional computational methods, even the best, biggest, baddest technique that is available to us in thermodynamic equilibrium is actually not something that can be straightforwardly generalized to systems that are driven far from equilibrium. And that, when I'm referring to systems here far from equilibrium, I'm actually referring to systems that these are non-thermal excitations. So we're not talking about something where I've just cranked up the temperature. Temperature is probably a disastrous quantity to invoke here, in fact. Okay, so a theoretical description of such systems, particularly quantum many-body systems that are out of equilibrium, is hard. Nevertheless, there are experiments. They probe it, whether they're optical probes, scanning probes, probes at various synchrotron facilities, and that's really a challenge for theory to go after. The workhorse of people thinking about excitations of this sort, in materials physics in particular, has been time-dependent density fluctuative theory. It's an extension formally of the ground state density fluctuative theory. However, it misses a lot of those non-trivial correlation effects that I alluded to a couple of slides ago. There are other approaches. There are non-equilibrium phase functions approaches. There are some of the diagrammatic techniques that I talked about, but none of them in their individual form is quite sufficient. So we're now thinking about how maybe you can combine across non-equilibrium dynamical mean field theory, which is good for these strongly correlated systems. It scales very poorly, together with some of these lower level theories. And there's a lot of work happening actually in how to combine these. And this is my next slide is going to be my last introductory slide before I dive into some data here. So the driven aspect is one extreme. The other is where we're thinking about cases where we want to invoke the quantum nature of light. We want to think about things from a quantum optical standpoint. And now, if we're trying to formally have both the quantum optical component as well as everything from a condensed matter standpoint retained, perhaps a simple model from quantum optics, a few level model is insufficient. So towards that, we've introduced approaches. And I should point out the photon is included, say, in GW methods or Bayes-Salpeter equation methods, where you think about optically excited quasi-particles, and you talk about, say, their binding energy, or perhaps even talk about biexciton and trion physics. However, almost always the photon there is classical. I'm thinking about incorporating that in a very, very classical standpoint, even if the electronic structure theory itself formally is quantum mechanical. So what we and a few people in the community have now been working on is a way to combine QED with electronic structure theory formally and also computationally. Electronic structure theories at different levels and their corresponding QED combined counterparts also at different levels. So this could be QED plus Hartree-Fock. This could be QED plus mean field theories. It could be QED plus time-dependent density function theory, or in some rare cases, QED plus coupled cluster. Coupled cluster, singles, doubles for all of my quantum chemists here is the gold standard, and I know we would love to do everything using CCSD and capture all possible correlations. That's not always possible. So some of the other approximations in conjunction with QED work out. Okay, so I'll come back to this here in a second. So I've told you a little bit about the various methods, that you could think of them as where methods have been introduced, where they also hopefully laid out a picture that candidly tells you where existing methods fail and where there's an opportunity to develop new techniques. So now we're going to go from methods to actually predicting stuff, predicting interactions, correlations, and I'll give you some examples of where we've applied extensions of techniques that we've been developing. Okay, that brings me to the outline of my talk. As I told the organizers, I have a very ambitious view of what could be accomplished in 1 hour. So what I'm going to try and do is go through linear and nonlinear interactions in various types of quantum materials. In particular, I want to tell you about some of the work we're doing in optically excited and quantum materials, nonlinear dynamics, nonlinear photonics, and also, if we get to it, hopefully also hydrodynamics in topological quantum materials. All right, so first part. So going from that very high level view of how you would think about QED and electronic structure, let me put some equations to it. So on the left, I have my full physical system, and this is a system that involves interacting electrons, interacting nuclei, and photons. Okay, nuclei serve two purposes here. A, I can talk about things that are in vibrational strong coupling, which is important. I can talk about vibronic states, but nuclei also present a very natural and yet physical way of incorporating finite temperature into the calculation. Now, this full interacting physical system can be mapped onto an effective cone-sham system. I don't have to have it be a cone-sham system. I'm doing this because I'm going to tell you that QED plus DFT can work in some simplified cases. I'm going to show you also examples of where that's not the case. Okay, so the mapping is in principle 1-to-1. This is something that's been known for some time. As long as I can find a worthwhile and physical mean fields exchange correlation kernel, right? So formally, this was derived in QED plus electronic structure in fully relativistic limit, and life was good. Today, let's just go to the non-relativistic limit. We're going to be looking at molecules and materials. So let's just make that approximation. This will have to be thought about differently if you have something with transition metals and strong spin over coupling. But just for the next few slides, let's ignore that. We're going to a simplified picture here where we are going to look for a 1-to-1 correspondence between things on the left and things on the right. Okay. So I have these internal variables. I have a time-dependent electron density, and I have a mode-resolved electric displacement coordinate on the left, and I'm mapping these onto the external variables, which are the time-dependent external potential and a time-dependent current. Okay, and I can do this. This 1-to-1 correspondence between internal and external variables is something that folks from an electronic structure context have done quite robustly, as long as I can find that mean field exchange correlation kernel. So we've been about doing this for some simplified molecules, and we've developed a simple, maybe I'm using the word simple here too much. It's simple because I feel like I want to do a complicated, cavity coupling to a superconductor, and it's doing something, and I want to look at these very complex experiments. And at the moment, this technique is something that can look at, say, a few molecules that are in a regime of ultra strong coupling to the cavity. So we've been able to track things like vibrational strong coupling, and just earlier this week, we put on the archive a paper where we find a cavity-mediated change in the chemical dynamics and attribute it unequivocally to a resonant mechanism. Those of you who've been following some of the experiments around this from Edison and others know that there's been controversy in the fields, and also know that previous calculations have not captured this resonant mechanism quite all that explicitly. So we've done that. I don't have the paper cited here, but if you look it up, you'll find it. It's already on the archive. And so we can look at things like different trajectories for molecules and figure out changes to quite complex chemical dynamics. This is not something you want to do if your molecule and cavity coupling is in a regime of weak or moderate coupling. This is definitely overkill for that. But in cases of strong coupling, this is the way to go. So experimentalists frequently say, that's great. That's a lot of equations. You're looking at some stuff, but show me some spectra. And the way to get to spectra is easy with TD-DFT. It's pretty well known for getting properties of excited states, even though it doesn't get all of those correlations right. It can give you a set of absorption or fluorescent spectra. So now I'm really looking for this component chi, I'm looking for the response function. Now, there are other methods for electronic structure theory that have been extended to this regime of electron-photon interaction. You can always do exact factorization. There are ups and downs to that. You can think about a conditional decomposition approach, as well as a cavity Born-Oppenheimer approximation. So what we do here, we have options. We can looking at this response function, think about an explicit time evolution, or we can think of being in the frequency domain. We pick frequency domain in particular just because we're not going to be memory limited going down to a couple of picoseconds. You don't have to worry about essentially having to artificially cut off the calculation because we're stuck in time. Okay, hopefully some of this is making sense. And I know it's Friday afternoon, and maybe looking at Dyson equations is not your favorite thing to do on a Friday afternoon. But let me just say that these are the two corresponding equations for those response functions that I'm going to be looking for, right? And now the first thing you want to observe is that I took my exchange correlation kernel and I split it up into two parts, right? So that corresponds to the two sets of Dyson equations here. And now I have a part that describes the electron-electron interaction and a second part that incorporates all of the effects associated with the electron-photon interaction. And then in the frequency domain, I have something that represents a matter block and something that represents electron-photon coupling, not to be confused with electron-phonon coupling. And I can go after this system, right? So one other thing, particularly in the case of how we treat the Hartree exchange correlation kernel here, exchange correlation functional here, we need a good description not only of the equilibrium position, but also of the extended nuclear configurations. We're still invoking a cavity Born-Oppenheimer approximation here. We can debate during the overtime about why that may or may not hold, but that's what we have here. But one thing we are taking into account is that in case of this very excited state manifold, even if a simple molecule could be a formaldehyde molecule, could be a benzene molecule, pick something from your high school chemistry, they all have states that go beyond the first couple of excited states. In fact, we need states that are a mixture of those Rydberg states as well as more localized valence states with the pi star type transitions. And card-carrying chemists will tell you that without that, describing the dynamics is insufficient. There are nice intersections between this work and the work of Shaul Mukamel, who's looked at manipulating various non-adiabatic dynamics at avoided crossings, and he's written some really, really nice papers on the ways to do theoretical spectroscopy on such correlations. Okay, so do I always have to be limited by this exchange correlation kernel, right? The answer is no, you don't. And in fact, we introduced this idea of photonic quasiparticles. And this might be a little bit confusing because I told you about polaritons themselves being hybrid light matter quasiparticles, and I'm calling this a photonic quasiparticle, but stay with me. So in this case, we go from a system on the left, right, where we have a bunch of the exact system with a bunch of virtual excitations of our matter and cavity system, and we approximate it with a few virtual excitations of this effective system. The name of the game in replacing the system on the left with the system on the right, so essential to our ansatz is the notion that we have an effective photonic vacuum whose modes are going to be different than the modes of the absence of light matter coupling. And if I can come up with a representative or useful ansatz to describe such a system, then I have a nice non-perturbative theory. The link here will, or the reference here will walk you through why we call this a variational method and exactly how we invoke the variational principle. But let me just show you the results associated with this. So now we're going to compare our approach, which is in blue, this variational QED, with exact numerical diagonalization, which is in the red dots, and maybe a more standard perturbative approach here, being these orange dashed lines. So to do exact numerical diagonalization, we have to pick a simpler system. We have about 50 photon modes in the cavity, a handful of photonic excitations, and we pick something pretty simple. We're going from a regime of no coupling to a regime that perhaps you could only realize in superconducting cavities. This would be not all that physical for your optical systems. Okay, so the first thing you notice is that in regimes of strong, of no coupling, everything is good, everyone agrees. As you get into regimes of strong coupling and ultra-strong coupling, our variational method and exact numerical diagonalization continue to agree, and they continue to agree across from no coupling to deep strong coupling, whereas the perturbative approach takes a different path. In fact, this is what I would lovingly call a major discrepancy. So we think that this method, and this method is very low computational cost, is something that can run on your laptop. So if you're interested in running some of these calculations, let me know. This is something that is a real space method. I haven't had a chance to talk about the advantages of doing that here today. But essentially, if you, it is a good non-perturbative description of things with spatial dependence, like the Casimir polar force, which you can get naturally out of this theory.
So, Pri, can I interrupt you for 1 second and just ask a clarifying question?
Yes.
It sounds like you're talking about virtual photons coming out of the vacuum. I know in the cold atom community, we're never strongly enough coupled for that to be a thing. Are we talking about virtual optical photons? What sort of parameter regime should I be thinking of?
Yeah,
is this that G is large enough that we're virtually creating optical photons because of the small load volume?
Exactly. So in theory, I can crank up the coupling. I can crank up the G arbitrarily. Of course, I know experimentally you wouldn't realize this regime in the same physical system where you're out here. I think in superconducting cavities, at least my understanding, I'm not someone who fabricates or experimentally works with them, that you can get into.
Yeah, you certainly can. Mm-hmm. I see.
So anything lossy. So my plasmonics friends pretty much live here with some experiments in plasmonics, or even these plasmonic tips that confine a single molecule. You might get into, say, lose my cursor, somewhere out here. So you might start to see deviations from standard perturbative approaches, but you wouldn't, it's highly unlikely that you'd be at that 0.94 number. That would be crazy from a optical system standpoint. But that's an excellent question. And actually, something that I'm personally looking for is a way that this approach can intersect with some of those other genres of experiments that are not motivated by looking at this vibrational strong coupling to molecules, but by a different physical realization. Okay.
Thank you.
So that's an excellent question. I'm gonna keep going and spend the next couple of minutes, right? So I use the word nuclei and vibrational a few different times. So in the world of condensed matter, that's essentially talking about phonon polariton. And a phonon polariton, something that any polar material that has a LOTO split should have some form of a phonon polariton, right? And then I can see things that look like branches, a lower and upper polariton relative to the light line, or technically the full cone. So there's a conundrum that a true 2D material, say your favorite 2D material, hexagonal boron nitride, at the gamma point, it does not have an LOTO split. So could a true 2D material still have a phonon polariton, and what would its coupling to an external emitter look like? So I'm going to tell you about over the next slides is a universal parametrization of a polar monolayer to describe phonon polariton. I'm going to reconcile this no LOTO split business. And then based on showing it for hexagonal boron nitride, I'm going to tell you that there's another set of systems like monolayers of ABO3 perovskites where you can similarly have interesting phonon polaritons. Okay. So there are many reasons to think about phonon polaritons, and one of them is that it provides you control of your parameter of the dynamics in the mid-IR. Losses don't hit you as hard in the mid-IR, and other things are possible. And one of the goals of the community has been to bring this really down to the atomic scale limit, and thinking about phonon polaritons in 2D materials, of course, is a natural way to do that. So even though you don't have this LOTO split at the gamma point in polar materials, in 2D polar materials, it doesn't mean that you can't have a phonon polariton. And we can show this microscopically. So we've actually made an attempt to connect the microscopic phonon properties with the macroscopic electromagnetic response to exactly reconcile this. So on top here, I have the conductivity in terms of the, so what do I need for that, right? So I need to know something about my photon dispersion. I need to know something about the damping, and yeah, that's pretty much it, turns out. So I can get things associated with the photon dispersion from my favorite experimentalist. I can also calculate it from my ab initio calculation if I want, and then I can take a long wavelength limit to come up with this parameterized conductivity of a general polar monolayer. And this actually gives me the properties of 2D phonons that are coupled to the optical fields here. And I can get various other properties of the phonon polariton after I have a good description of the conductivity. I want to point out that we picked to describe this in terms of conductivity. We think it's more physical than talking about epsilon that is squished down to a monolayer. I know that there are some active debates around whether sigma or epsilon are more physical and faithful quantity here. I'm not going to address that part of this debate here today. Okay, so using our parameterized equation there, what we can do is predict the properties of phonon polaritons in a simple monolayer of hexagonal boron nitride. We can compare that to the bulk. So you look at the real and the imaginary part. This is a fairly standard thing that folks do in optics, and you can look at it for a few different loss rates. You can look at the ratio of the real and imaginary Q. But more importantly, I think it's good for us to look at the dispersion of the monolayer here. This is, by the way, something that following our predictions, again, working closely with Dmitry Basov, we were able to realize experimentally that the dispersions tracked our predictions pretty well. And we were able to look at a distinction between a monolayer and two layers. Work that I'm not going to talk about here today involves things like how do we use these phonon polaritons as a diagnostic in twisted HBN type structures. Everyone likes twisted systems, but we're just going to skip over that this afternoon. Okay, we building on that can look at how you can get into regimes of strong and ultra strong coupling to disks of HBN, for example, and I think that there is actually a pretty fun opportunity here for doing quantum optics with phonon polaritons, hoping that some of these ideas that we put forward will be experimentally realized soon. So I told you that all of that for HBN was somewhat of a benchmark to show that all of this works for a system that is common and understood in the field. We can also predict things for systems where phonon polaritons have not yet been measured. And this is where we were really encouraged to see a monolayer of strontium titanate synthesized by the group of Harold Wong at Stanford in 2019. And we said, here we go. These are systems that have strong IR active phonon modes. Maybe every ABO3 perovskite could actually allow us to bring phonon polaritons into a different regime of operation where HBN doesn't go. And a couple of things about STO. Some of you might be familiar. This is a very fun system for people in condensed matter. Lots of things happen in STO. It does have special phonons, not only ones that can couple to the optical field, but also ones that are implicated in this out of plane coupling with monolayer superconductors. There's a whole set of people who are now thinking about how iron selenide modified by strontium titanate does interesting things. So I won't talk about how that phonon and stuff can couple out of plane, but I will say that the phonon polariton could be used as a way to both probe that out of plane coupling, but also as a way to control it. So you could think about squeezing this phonon polariton, for example, and manipulating it in order to actually change the coupling of STO to a monolayer superconductor. So we've looked at what these phonon polaritons do, and this is my last slide on the first part of my talk before I'll take a few questions and go to the next part. So we've looked at how the dispersions are similar and yet very different from HBN for STO, for lead titanate, for potassium titanate. We've also looked at, I'm not showing that on this slide, how all of this behaves in lithium niobate. They all appear to have interesting photon polarity. Lithium niobate, also known for many of its non-linear properties. I think there's a bunch to do here. And I hope some of you will go and experimentally try these things out. Okay, so I was next going to talk about some of our work in thinking about defects and then going to driven nonlinearities. But I think I might just go directly to the driven nonlinearities, just looking at the time. But before that, maybe I can take any questions if things come in.
Great. Thank you, Pri. We have a number of questions. I'll just pick a couple of them for you. One is when doing these QED, TDDFT calculations and simulations, how many experimental inputs do you have? Are there free parameters that you tune around to get good agreement with data expectations, or is it all sort of first principles?
The calculations themselves are first principles. The one thing that we can arbitrarily crank up in our calculations that would not be easy to do experimentally is the coupling. So we can do that while, if we want, ignoring the losses. So we have in calculations included the losses. So all the calculations that we're showing in the paper I alluded to that we put on the archive earlier this week, those don't use experimental parameters, and none of the work that was cited here uses experimental parameters. So the one sleight of hand, of course, is that we can crank up the coupling. And I'm sure experimentalists will say that's a big sleight of hand.
Well, but it's a good incentive and motivation for experimentalists too, right? So there's value in that. Here's another question. How about the multi-reference effects, aka static correlation, which are known to be hard to describe even with the gold standard of CC-SDT? Is there any hope that these effects will ever be within reach of these sort of combined ab initio methods that include cavity QED?
Oh gosh, okay. So keeping a multi-reference states is something that is super important, including for the part that I just skipped over with thinking about these optically addressable spin qubits. I think without having the multi-reference component there, you're certainly making approximations. It's very hard to incorporate that even without this coupling to the photon. So I don't see an easy way to do it. There is a lot of talk of various embedding theories that might get us there, and there's talk of how basically embedding here being you treat different things at different levels of theory that you stitch together. You can think of it as unpacking layers of an onion, or pick your favorite, or Russian doll. Well, pick your favorite analogy, but that's roughly the idea. It still assumes that you can formally kind of merge across those levels of complexity. So there is talk of trying to do that in the field of polaritons. I haven't seen anything yet, but we and others I know are trying. So excellent question. And whoever asked that question, if you have extra bandwidth, you want to give that a shot, you want to work with me on it, let's do it.
Well, because you actually like that question, I'll tell you it's from Timur Cherbil. If for the questions that you don't explicitly compliment, we will keep the names of the victim secret. Okay, I actually have one more clarifying question, which I think may be a language difference between communities. What defines a cavity Born-Oppenheimer approximation to you?
Yeah, so it's an extension of the conventional Born-Oppenheimer approximation to incorporate. So, okay, Born-Oppenheimer approximation allows us to say that nuclei responding at a different time scale than thinking about an electronic subsystem. The cavity component there is a generalization that essentially allows you to think about strong coupling to one or both of those subsystems without saying we are formally beyond the Born-Oppenheimer approximation. Okay. Does that answer your question?
So is this saying that the sort of the photonic cloud adiabatically follows the atom around? Is that how I should think about it? Okay.
Yeah.
Great. Okay. We do have a number of other questions, but I think some of them may be clarified by the next section. So I'm inclined to leave them for now and let you continue. So thank you.
Okay. Awesome. Thanks. So everything I've shown so far is in this regime of few photons, some cases, no photons. Let's take the other extreme where I'm driving the system and I want to look at things, for example, that happen harmonically. So photons are a really good example of this, right? So nonlinear interaction between different photon modes can do really amazing things to various vibrationally excited solids. And there's a real opportunity here to think about various different nonlinear photonic processes that then change some other order in the system, okay? And so here's what I mean by that. I can pick out a particular photon mode, I can drive it, and I can change the effective electron-photon interaction, which is very important because maybe that's a way for me to control the superconductor via changing something that is driving just the lattice. Or even if it is, say, the magnetic order, I can drive the lattice. You know, it's basically the visual I have is I have a giant hammer and I'm hitting it very hard on some kind of bell, and it's making the system go out of equilibrium. And it's not just changing the properties of the lattice by itself, but it's actually changing the properties of the entire system in the process of it happening. People have done really interesting work in this area. Andrea Cavallari, Asashi Mamago, and others are thinking about how this can be used to either control the behavior of superconductors. K3C60 is the poster child for this. There are other examples that have shown up. And part of that interest goes through the various different processes, the photon processes that you can excite. So some of you may have seen these acronyms before. If you haven't, I'll just kind of walk you through them. They can have these different frequency onyx Raman scattering type processes. You can have parametric Q4 or parametric Q3 processes. You can also have some frequency onyx Raman scattering. And to resonantly drive, I need that first photon mode to be something that is optically active. So whenever somebody says, I picked out a good mode, right? So what they really mean is that it's a good mode from a resonant condition standpoint, and it's something that I could drive using the source that I have. Now, that might not always be the case. You could maybe have something that is slightly offset. So you could use coupling to, say, a terahertz cavity in this case to actually do some of that redistribution of vibrational energy. And this is something that, of course, leverages the fact that once you couple the cavity, maybe you're going to get these upper-lower polaritons. That's going to allow you to overcome that energy matching condition, but also maybe the cavity is going to allow you to couple in a lot more energy into this particular material, maybe allowing you to further change the behavior and control the non-equilibrium properties. Sorry. Okay, so let me give you an example of where we've shown that you can actually get Higgs-Goldstone dynamics by picking out a photon mode in a nice model system. It's a hexagonal manganite. Details of it don't really matter explicitly. All that really matters is that it's the structural dynamics are what gives the order parameter. So you essentially have the structural dynamics here as follows. I'm going to use my hands to describe this. I have a tilting of the bipyramids, the manganese oxygen bipyramids here, and I have a buckling of the indium atoms that look like they're in the middle. Okay, so that's my interpretive dance of what this structural dynamics looks like. And if you map that out, I get this nice potential energy surface. And now I have my conventional Higgs and Goldstone-like photon modes that modulate the amplitude and phase of their primary order parameter, respectively. Okay, so in this case, what we find is that the Goldstone mode in particular is optically silent, but the Higgs mode is not. So by exciting the Higgs mode, I can actually get to this optically silent Goldstone mode, and this is actually because of a nonlinear coupling to that infrared active Higgs-like photon mode. Okay, and so we look at this explicitly. We do some of the time dynamics for this. This is a combination of ab initio as well as phenomenological modeling, and what we see here. So at the top, for a conventional optical picture, you'd say, okay, show me when the pulse comes in and show me the excitation of the Goldstone mode. So in green is the terahertz pulse. It excites a Higgs mode, and you see a few picoseconds later, I see the emergence of that Goldstone mode. And these are, this is a coherent excitation. And this is, I know from AMO standpoint, also there are observations of such Higgs Goldstone dynamics. So one of our motivations here was to actually figure out if the dynamics in such structural order parameters look similar to or somehow diverges from the picture that people have seen in AMO. We haven't fully answered that question, but so far what we're finding is that there are many, many similarities. So from an energetic standpoint, I have all my energy in the Higgs mode, and over time it goes into the Goldstone mode. Then we look at it actually using both. So we have the corresponding line width of the Higgs mode and the line width of the Goldstone mode. And what we find is that, yes, this process will be coherent. So you do actually get this coherent transfer of energy. It's not going to be line width limited is the point. And this is something that can be realized at very moderate fluences. This is something that is accessible experimentally. So the same dynamics, something that we're now looking at in systems with more complex order parameters and not just a simple interpretive dance of the order parameter, though I am working on finding one for some of the magnetic systems as well. So we were excited about this and led by one of my postdocs, Dominic Jurashik. He, by the way, is starting his own group at Tel Aviv University this fall. He said, actually, there's a whole spectrum of optomagnetic and magneto-optical effects that can emerge with just replacing the word opto with phono. So if I can find good phonon modes, I can actually get things like equivalence of the inverse Faraday effect. I can get a phonon inverse Faraday effect, and I can similarly write down an effective magnetic field that is a phonomagnetic field rather than an optomagnetic field. So there's a whole table of these that we've shown and systems where you could realize this. But the easiest one to look at is nickel oxide. Okay, so nickel oxide, if you haven't followed the work on the magnetic system side, is a good fruit fly for people in the field. And usually the electromagnetic components of the laser pulse would couple to electronic degrees of freedom of the magnetic ions. This would give you this notion of ultra-fast optomagnetism. And this is something that has been thought about now for a decade or so, maybe even longer. More recently, folks have seen that you can actually have this light coupled to the spins directly by exciting some coherent vibrations of the lattice. There's an experiment as well in 2017 that looked at the inverse Faraday effect with an effective magnetic field that was fairly mundane, maybe on the order of 28 millitesla. So I can also do the same with nickel oxide. I can drive it and get some tiny magnetic fields. And then we realized that the limiting factor really is how large is my spin phonon coupling. And this is where Dominic sat down with a set of old tables from the 70s and 80s, and somebody had comprehensively tabulated, I have no idea why, the various spin phonon couplings that they measured in the context of producing these tables. And there we found our perfect system, which is, or one of our perfect systems, is cerium trichloride. It's a rare earth trihalide where you can get very large effective magnetic fields because of the circularly driven photon modes acting on the paramagnetic 4F spins. And that led us to realization that actually there are very many systems that have these paramagnetic 4F spins. There's a whole kind of set of rare earth trihalides actually where this would be possible. And using this system as our model system, by the way, this is a nice model system because the primitive cell has like 8 atoms and you get about 21 optical photon modes. I can tell you their irreps if you're interested. So here we looked at the coherent photon dynamics with the excitation from a terahertz pulse. And actually we find that you can get giant effective magnetic fields in the system because of those 4F spins, because and that you can polarize these spins with experimentally very accessible pulse energies. And this we think is going to be quite general. might even be actually useful for control of the induced magnetization, for people working in for magnets, for electrics, and other types of magnetic heterostructures. So we're taking this idea of dynamic control of quantum matter, cavity control of quantum matter, and really thinking about various non-thermal, non-equilibrium phases that you can get in these further. So that's really kind of the idea here. So questions on that before I dive into hydrodynamics?
Okay, we have a couple of questions here. So I guess one question, are there qualitative behavioral differences that would make one want to say use phonon polaritons versus electronic polaritons as a tool for nonlinear optics?
Yeah, spectral band. I could be in the mid-IR, I could be in areas where doing optics with conventional approaches is hard. This is a way to get there.
I see. And how about in terms of thinking about the strength of the nonlinearities? Is there hope of getting to like a single photon kind of nonlinearity?
That's the hope and dream.
And what's the limiting factor experimentally for that? Do you know? Is it the cavity cues or the phonon cues or?
Probably a combination of the two. I think the highest nonlinearities people have seen are maybe from the IBM Zurich group in barium titanate, I want to say, something like 1,000 or even more. Yeah, I don't really know. Actually, let me reframe that question. And I know you didn't ask me this, and I'm giving myself a harder question, but what is the fundamental limit on that nonlinearity? And I don't have a good answer for that.
Yeah.
I don't think it's a fundamental material limit. I don't think we're anywhere close to the fundamental material limit, let's say.
Interesting. Okay, thank you. Okay, here's another question. For the Higgs-Goldstone dynamics, what's the experimental observable that would allow you to say observe the excitation of the Goldstone mode? Is this like a pump probe type experiment that you have in mind?
This is terahertz pump probe. Yeah, it's terahertz pump probe, and actually this ringing, right, that you see for the excitation of the Goldstone mode is what you'd expect. There is a whole field of people who are using this kind of Higgs spectroscopy, by the way, to characterize the behavior of superconductors. I haven't had a chance to talk about that or collective mode spectroscopy today, but I'll just say that actually looking at such Higgs-Goldstone dynamics is something that people are proposing as a way to characterize the nature of superconductivity in some unconventional systems. So
was that one? I'm sorry, go ahead. Okay, I apologize.
No, go ahead.
No, if you should finish your answer. I
was going to say, we also we put out this thing on how you could use such collective mode spectroscopy and looking at these Higgs modes actually as a way to characterize time reversal symmetry broken superconductors, including very controversial ones like strontium-ruthenate and UT2 and UPT3. We got a lot of flack from people saying, well, all these signatures that are in these spectra that rely on predictions are very unreliable. There has to be a more smoking gun signature. So we're trying to figure that out. But some of the same Higgs-Goldstone dynamics actually show up in that context as well.
Thank you. So was that one a good question? Because
yes.
If it was a good question, it came from Shimon. If it was a bad question, it came from Norm. Okay, so there are actually several other questions. But since we are running a little bit low on time, I think we'll just let you tell.
Okay, I'm going to speed up. I'm going to speed up the action here. Okay, so we're going to look at hydrodynamics in topological materials. For my photonics friends, this is maximally confusing because a hydrodynamic picture is frequently invoked to describe things like collective excitations and these types of plasmonic systems and such. So I'm sorry if I've ever confused you in our papers, but now I'm going to actually talk about hydrodynamics, like the kind that shows up in a fluid dynamics course. And I'm trying to convince you that hydrodynamics in topological materials looks fundamentally different from hydrodynamics in graphene. They're both independently exciting, but their reasons are different. And we like topological materials in my group. We not gonna belabor that too much, but they have interesting stuff that happens. And hydrodynamics is a subset of the interesting stuff that happens in topological materials, but it's one that actually requires us to, from a theory standpoint, think about spatially resolved transport. And I'll show you a slide on some of the methods we've introduced towards that here in a second. So electron hydrodynamics is pretty cool. So if you think of a typical conductor and you think about the picture from Astronaut Merman or your favorite solid state textbook, you'd say, well, electron flow is diffusive. Electrons will scatter off impurities, lattice vibrations. It's going to look like balls in a pinball machine, and I'm going to get momentum relaxation. And momentum relaxing processes are not going to give me collective flow. So, Pri, what are you talking about? There's what hydrodynamics, right? Typical conductors, even if they're really good conductors, seeing hydrodynamics is going to be hard. But in the presence of strong electron-electron interactions, electrons can actually flow collectively. They can start to look like a fluid that actually is similar to, say, thinking about molecules in a classical fluid. And these are momentum conserving interactions that are really dominant. So when I say electron-electron interactions, the first thing that probably comes to your mind is the Coulomb-mediated electron-electron interaction. And something I'd like to convince you of here today is that actually the phonon-mediated electron-electron interaction is what is dominant for hydrodynamics in these different topological materials, and we've seen that in a few different cases. Okay, but I digress. Let's talk about hydrodynamics a little more generally for a second. So we care about conserved quantities, and the beauty of hydrodynamics is that it actually offers a universal picture of such collective fluids, which means that I can invoke descriptions that should involve maybe more universal quantities like viscosity and things that really are reflective of classical fluids, which is what was done for graphene. And there's really pioneering theoretical work by Leonid Levitov, Christian Falkovich, Adi Stern, and others towards that. So hydrodynamics really is a tale of two different length scales. I have a set of momentum relaxing processes. By the way, now I need to think about all of those microscopic processes, right? And bin them into momentum relaxing and momentum conserving. It's like, people have to pick whether they're team A or team B. But there's also another length scale that is relevant, and that length scale is the geometry length scale. So without thinking about an explicit geometry or thinking about an actual length scale associated with what we are either patterning or how we are observing hydrodynamics, it doesn't make sense to call it hydrodynamics. Well, I actually need that. But the other component that is super important about hydrodynamics is that it shows up in the spatial profile. Okay, so this is not something that would show up in it would show up, you just wouldn't be able to resolve it in a transport measurement where everything, all spatial information is lost, or from a theory standpoint, a transport method where you lose that spatial information would not be able to tell you about these different types of flow. So there's a Gurji regime, there's the Knudsen regime, the porous, the diffusive, and combinations thereof, depending on which process is dominating. Right? So everything, those microscopic processes give us a set of length scales. Those length scales then allow me to think about these competing length scale pictures. So what I'd like to do is come up with a spatially resolved picture of the hydrodynamics, and better yet, because I have these three length scales, I want to come up with transport phase diagrams where I can tell you this is where I have peak hydrodynamics with this LMR and LMC normalized by that geometry competing with each other. And that's something that involves both those microscopic processes as well as the transport here. So we developed methods. So the experiment here will be experiments from Uri Bol and Asaf Hama, who are both going on to start their own group. This is scanning NV magnetometry at variable temperatures, the technique they've developed here in Mary Kobe's group, as well as the theory here by Yashin Wang and George Barnavides. Yashin is also going on to start her own group at IOP China. Basically, I'm telling you, if you're looking to apply to my group, now's the time, because this is going to be a lot of people starting their own groups soon. Anyways, so these transport phase diagrams allow us to then think about the, so there's peak hydrodynamics, and then there's what the curvature would look like in these transport phase diagrams. So I want to have a chance to walk you through why we picked transport phase diagrams and everything that's associated with this. But let me just get to the punchline. So we looked at a system, tungsten ditelluride. Lots of physics happens in tungsten ditelluride, but in a few layer format, it could be a semi-metal, it could be a Wild semi-metal type 1 or a type 2 Wild semi-metal. In its monolayer format, it is believed to be an unconventional superconductor, but in a monolayer format, it also cannot mathematically host the model physics. So let's look at the temperature dependence, right? So we find, and we can look at each of these processes from an ab initio standpoint. We can look at their behavior across a broad range of temperatures. And we basically wanted to look for this crossover type regime where you have a particular process that is momentum conserving, that dominates over all else. It's from a time scale standpoint, it has to be the one that sets the time scale. From a length scale standpoint, it has to be a really, really long length scale. So the mean-free path that falls out of that particular microscopic process has to dominate. And we pick the empirical part here is picking this impurity length. So we can tell you that for Claudia Felser, these samples are from Claudia Felser. So these are in the ultra clean limit, but they still have some impurities. And where that impurity line is really what sets how clean or ultra clean the limit will be. Anyways, so we can predict what happens in tungsten ditelluride, and I think, conclusively establish the origin of hydrodynamic behavior in tungsten ditelluride. In particular, so on the top here is the experiment. You're looking at so the MV magnetometry gets the magnetic fields, and you get the current profiles from there. And on the bottom is our theory predictions for the same system. A few things that are hallmarks of hydrodynamic flow: A, the phase profile, and B, the non-monotonic temperature dependence associated with with this system. And we actually get very quantitatively accurately the region of peak hydrodynamics. Okay, so the way to think about this is that there's a regime where I'm going to have normal diffusive flow, probably a regime where I'm going to have something that looks ballistic. What I want is to be able to have a reasonable temperature range where I see hydrodynamic flow, which here is in the tens of Kelvin. For those of you who do low temperature physics, this is very balmy temperature. And actually, we predict where you would see this peak hydrodynamics. So this was in part made possible by a theory technique, a computational technique, I'm sorry, from my student, George Barnavides, who's looked at spatially resolved non-equilibrium transport. This is a method that we are making available broadly to the community, so where you can take all of those diagrams that we predict and put them into our transport framework and get nice spatially dependent quantities. Okay, so what we find is that the hydrodynamics of the system cannot be explained by the Coulomb-mediated electron-electron interaction. Yes, you have strong electron-electron interactions, and they are phonon mediated. We established that, and now there are interesting questions in knowing something about hydrodynamics in this system. What does that tell you about the nature of superconductivity in this system and the monolayer limit? And also, there are from folks like Samir Sachdev here, implications of hydrodynamics in the descriptions of superconductivity. So knowing something about superconductivity, knowing something about hydrodynamics here might tell us something about superconductivity as well. Okay, and this work should hopefully appear soon in Nature Physics. Do I have 10 seconds more, John?
What I would say is like a minute or less we can do, but if it's a longer story, I would say you should just advertise it and we can chat afterwards.
Okay, just give me a minute and then I'll be done. Okay, so everything that I told you for thinking about fluid flows here is from a microscopic standpoint. But the beauty of hydrodynamics really is that universal macroscopic description. And the way you go about doing that is thinking about viscosity. Viscosity in the context of graphene was approximated to be a single number. And that just turns out because graphene is incredibly isotropic, and there was a set of luck associated with that. But we started exploring the general rank 4 tensor for the viscosity here. and actually very quickly realized that if all I do is constrain the viscosity tensor by thermodynamics and the crystal symmetry, but in some cases I look at time reversal symmetry being obeyed, some other cases time reversal symmetry being broken, I come up with lots of interesting types of viscosities, including a dissipative term, a Hall viscosity term, as well as a vorticity term. Realizing, and I'm running through this now, but realizing that actually in particular types of symmetries, if you could create a Corbino disk type of geometry, this is something people do commonly in fluid dynamics, you could actually get steady state vortices in specific types of crystal symmetries. So this is an area where we're now starting to think about anomalous viscosities. If you like unusual viscosities, might be easier for me to say, and the implications of that for transport in various low symmetry materials. So name of the game here is low symmetry, and where possible, break time reversal symmetry as well, and you'll find interesting phenomena. Okay, so yes, there are other systems that do this. We've studied it. I can tell you more about this after. So let me just summarize and say I told you about our work in predicting light-matter interactions, a little bit about how optically excited systems behave in various regimes, and also a glimpse of our work in hydrodynamics. Thankful to funding, in particular to Department of Energy and to the Moore Foundation, both of whom have been incredibly supportive and patient with us. And thank you to members of my group again, and to you for spending Friday afternoon with me. So happy to take any more questions.
Thank you for a lovely and engaging talk, Pri. So we have a few additional questions here. A first one is sort of a little sharp, I guess. Given that one can explore hydrodynamics with fluids like water, what are the benefits of exploring it with electrons? Is the idea to try to get emergent classical transport coefficients from first principles quantum theories? Is the idea that there are interesting device application kind of things?
Yeah, kind of all of the above, right? So one of the simplest things that I can point to is that knowing something about the microscopic behavior of these topological materials is, this is a different way to understand the interplay between topology and transport in these systems, right? So this is different from purely thinking about a topological classification. So that's one answer. Yes, it has implications, right? I can think about device geometries where I can have essentially, well, momentum conserving flow, i.e. also very, very low on dissipation to the environment, and that has some implications. So I tend to be also motivated by things that could upend conventional thinking. So I just want to point out that finding hydrodynamics in correlated topological materials is surprising. It's a classical phenomena that shows up in the most quantum locations, and that's worth understanding. It's worth understanding what that tells us about correlations in these systems, and there are more theoretical and abstract predictions out there that hydrodynamics in these systems has fundamental implications for other types of physics. So there are mappings for other types of physics that shows up in these systems. So I alluded to that link between high TC superconductivity and hydrodynamics. That's an example of the type of thing where knowing something about one tells you something about the other. So tungsten telluride is a good example of that. Nature superconductivity in this monolayer is unknown, and this is maybe something that could shed light on that part of the problem.
I think another.
That's a good question, and I appreciate that immediately the link between hydrodynamics and usefulness is not apparent.
Yeah, no, I mean, I we just try to keep it informative. I appreciate that. Thank you. Here's another sort of I think interesting and perhaps basic one that I thought was nice. It felt like you're drawing a distinction between hydrodynamics and diffusion. right? But isn't diffusion a property of hydrodynamic systems? So can you say a little more about that?
Yeah, I was trying to say that there are regimes of hydrodynamics and the type of fluid profile that a basal flow that you expect, which is a hallmark of hydrodynamics, is different from a regime where you would have primarily momentum relaxing processes dominate. So that's the distinction here. I think where diffusive ends, hydro starts, hydro ends, ballistic starts, like these are not sharp phase boundaries.
Okay, thank you. Okay, one more question here for you. And this one is from me, so I really feel like it's a good one to end on. Very high quality question. So, you know, as a cold atom kind of person, I would say one solid state platform I've been very curious about understanding better is these copper oxide Rydberg excitons. So, you know, have you thought at all about those? Are there challenges to modeling those? I've
thought about them. I haven't done meaningfully anything there, so I don't want to comment on the challenges of modeling something that I haven't tried too hard on, but it is certainly a system of interest.
Great. Okay. Well, thank you very much, Pri. So two more things. The first is that the link to the post-seminar discussion is now posted in the chat. So anyone who has more questions for Pri should certainly feel free to join us there and ask. And additionally, I got so engaged in the discussion that I actually didn't prepare the slide, but Shimon has been good enough to do it for us to remind you of what next week's talks will be, both for VAMOS and for the quantum science seminar.
Just have to unmute. So yeah, next week, the VAMOS talk will be Martin Centurion from University of Nebraska-Lincoln, talking about imaging ultrafast dynamics in molecules with electron diffraction. And then the quantum science seminar will be on Thursday, and that'll be Vahid Sandagar from MPQ, talking about molecular quantum optics.